right, guess we can get started. So just were the first two lectures okay? Everybody good? Should we go over anything from there, slides or anything like that, or we're good? We're all good? Okay, great. Um, the material from those two lectures will appear on the first problem set. Um, but if you have any questions about it, just either email me or you can stay after today. We can talk about it. I just wanted to reiterate that this book here, The Essential Physics of Medical Imaging, is a really good resource. A lot of the diagrams and explanations for what we're going to look at actually come out of this book. So I just steal them. And if there's a chapter you should read in that book, I put it in the files component. So I hope you've figured out that virtually everything is under files. And there's additional reading, the homeworks, the lecture slides and things like that are all under that rubric there. And then the basic outline for the course is under this section of the front page, what we're going to do each week, and then some references for background reading. If the reading is strongly suggested, I usually put it in there that it's strongly suggested that you read it, but some of the papers are just for your own interest. And in trying to figure out your own interests, you're also trying to figure out what you're going to do for your project, right? Because that's the main sort of evaluation that we're going to do is sort of you take on a project, execute it, and present it to the group. And I'll post up, if it's not already posted up, videos of some of the really good projects from previous years, so you get an idea of what does it mean to have a good project. But principally, you're going to use some kind of analysis on a set of images or on something like that to derive a finding. Maybe you want to look and say, does left ventricular function track with left atrial function? Can I get dynamic data to look at those two parameters, figure out how to analyze those two parameters, and then prove that point that they're highly correlated or something. So, but there's a list of good projects over the years, and I can hook you up with that. Okay. Coming to class is not compulsory. You don't have to be here live. If you want to watch the lecture after the lecture has happened, they're all going to get posted up on YouTube, and they'll all be open. So if you prefer to listen to a lecture in 1.5x or 2x, it's fine with me. But if you want to ask a question during the lecture, it's obviously to your benefit to be here or to be online, one of the two. But otherwise, I don't have any, stipulation that you have to show up. You do have to show up once we start presenting your project. Okay, so you'll come and you'll make a presentation. Well, let me give a caveat there. It depends how many presentations we have. Sometimes it becomes more efficient to do it on Zoom, actually, that everybody just lines up their presentation and away we go. So we'll figure that out once we stabilize how many people we have in a class. Okay, that usually comes out to about 15, 20, something like that. So it's not a huge number. The project has two components. One is a presentation. That's the final presentation. And the other is the proposal. So the proposal you put together and say, this is what we're going to achieve with this project. This is why we're picking this topic, etc. All right. So with that, I think we'll start. So this is lecture 3, which is introduction to how you evaluate image quality. And I think everybody has a practical knowledge of what image quality is, just from the fact that we're all very good photographers now with the cell phones we have. You can just look at a picture and say, is this a decent picture or not, right? And the two major sort of features of a picture are, what is the spatial resolution i.e., was I able to resolve what I was looking for? And the other oftentimes is, what are the artifacts in this picture? And so with your cell phone, if you're like, I don't have great eyes, and so I'll look, there'll be some street sign far away, and I'll bring up my cell phone and take a picture and then zoom it up and see if I can read the street sign, right? Or read whatever it is that's far away. And so when you zoom that up, if you have achieved enough spatial resolution, you may read the word that is the street sign, right? If you haven't achieved enough spatial resolution, you all know what that looks like. It's like a blurry feature that you know is a word, but you can't sort of distinguish the different letters, right? You don't have enough spatial resolution. It's too blurry. The other thing is you could have hand shake, although remarkably, new phones actually compensate for your hand movement, and they will correct it automatically. That's why your pictures all look so clear. It's not because you have amazingly, calm hands. It's because electronically inside they're correcting the motion artifact. But if a car is zooming by at 60 miles an hour, you're not going to see a stationary car unless you put a really high speed shutter. You're going to see a blur, and then whatever is stationary will be clear. And so that is motion artifact. That's a blur, right? So how you quantify those things on pictures is what we're all about. As engineers, to provide images to radiologists, we want to provide them with the best picture possible. And sometimes we're going to evaluate, I could use process A or I could use process B to try and present to this radiologist images of patients' livers to determine whether or not this patient has a metastatic tumor in their liver. So that's like a task and so every optimization of an imaging protocol usually is associated with a task. And unless you do that, the space is too wide to optimize how you would get the best protocol. So usually you need to define, what is it we're trying to learn here? And oftentimes it comes to a binary decision, right? So all of this complex engineering and billions of bits of data boil down to a radiologist saying, disease is here. There is liver metastasis, or no metastasis, no disease here. So that's a bit, right? So everything boils down to one bit. And that's the decision made by the radiologist or the cardiologist to say that thing is here or not. Sometimes that task can be slightly more complicated, like, does this heart actually respond appropriately to stress? So you'll put a patient on a bicycle, or you'll inject a drug into their vein, which challenges the heart, which makes the heart beat a lot faster or with higher contractility. And you'll watch a movie of their heart and say, did that heart respond appropriately? So that's a more nuanced thing than one bit, right? So you have to look at all different sort of features of how that heart is contracting and how it is failing if it's failing. But when we go all the way down to like the nuts and bolts of what a picture is, one of the things that we want to achieve is a mathematical description of the spatial resolution of your imaging method. And so one way of doing that is, I think I can just, if we provide our imaging system with a point stimulus, just one dot. Say, let's go back to our camera. I take a picture of that back wall, and it's a uniform off-white picture. Every pixel should be the same. It's the uniform off-white. And now I take a pen and I put a dot on the wall. And I take another picture and ask, what does that dot look like in my picture, in my imaging system? What does it turn a tiny little dot into? And so here's our dot. It should be a constant signal at one position in space, right? But what you actually see when you zoom in and zoom into the image is not a single delta function or sharp pixel like that. It comes out as a blob. And that blob gives you the spatial resolution of your system. If you don't get a blob, if you get a disk, then your dot is not small enough to test the spatial resolution of your system. If you get a disk image, like it's a circle, you need to make a smaller dot, right? So you keep making the dot smaller and smaller and smaller until finally you get a picture that looks like this. It's what's called a Gaussian or a blob, and oftentimes it's modeled with a Gaussian function. And the width of that blob, so say it's full width at the half maximum. So here's the peak, and down here is like the half maximum. If I look at the width there, that tells you what the spatial resolution is of that system. That's a number that will give you an estimate of the spatial resolution. So if that width here is 1.3 millimeters wide, right here, you could say my full width at half maximum of that blob is 1.3 millimeters, right? And that tells you what your spatial resolution is. This function itself is called a point spread function. It's when you feed a point into the imaging system, what comes out. And it's this, usually a Gaussian blob. And so you can mathematically describe what that is, right? And it'll have a full width at half maximum is what comes out. Ideally, it's symmetric, i.e. the resolution in this direction is the same as this direction. Doesn't have to be true, though. We can have detectors that are finer resolution in one direction than they are in the other. So you can have this asymmetry in the spatial resolution. And obviously, for simplicity and just showing it, this is in 2 dimensions. So that's one picture. But in medical imaging, virtually all the time, we're doing 3-dimensional estimates of what's inside a patient's body. So the image you should think of as a volume, and it will have dimensions in X, Y, and Z, right? So it's going to have, it'll be a 3D blob, okay? And so we'll evaluate that. Any question about that? So that's the definition of the point spread function, okay? For a CT scanner, the way we get a point spread function is we put an extremely fine metallic object in the scanner. So if we're just doing 2 dimensions, X and Y, we could take a wire that is, some metal, and maybe it's 50 microns in diameter, right? So it's like a metallic line that's 50 microns in diameter. That's well below what the resolution of the scanner is, and it will produce a signal that looks like this. And you can measure the width of that signal. Another way of doing it in 3D on a CT scanner is we will take one of those really nice Japanese Pentel pens that are sort of a 0.3 millimeter ballpoint pen. Is the super fine one. And so when you write with it, you get these tiny thin lines. So we'll just break that and take that ballpoint out of the ballpoint pen and put it on a piece of tape, put it in the scanner on a plastic phantom, just tape it on there, and it'll be a very bright dot. And that dot is 0.3 millimeters, which is below the resolution of a CT scanner. So it will create this Gaussian blob, right? So that's how you do it. Mathematically, here's a 2-dimensional point spread function. It's zeroed here. It climbs to its peak somewhere in the middle. There's also a line spread function. So if I have a piece of metal that's in the XY plane and it's running down this way, I'll get this sort of Gaussian, 1-dimensional Gaussian as I cross the line. And then the other way you can evaluate it is if I have a phantom that has, say, plastic and then a very sharp wall and it turns into air or metal or something quite different, then when I come along here, and let's say this is air, and then this is plastic, and the wall itself is absolutely, vertical, then this edge spread function or edge response function can be measured as well, right? And all of these are related to each other. You can derive one from the other. One thing you can do, and this is done a lot, is you can trade off essentially noise for spatial resolution. And if we think about it, say we have a set of pixels in an imaging plane, right? They will have their estimated value for what's in the patient at that point, plus or minus some random noise. And the random noise comes from different sources. So in magnetic resonance, the random noise comes from the patient. So when you take a magnetic resonance image, you receive radio frequency energy from the patient using an antenna, and you put the antenna on top of the patient as close as you can to the target of your imaging. When you look at the signal that is coming out of that antenna, if you take it away from the patient and you look on your oscilloscope, you'll have some random noise. So that antenna is basically like a resistor. And so it has Johnson thermal noise, it's called, like molecules are jiggling around inside that thing, and they will just create a tiny voltage, even though there's no signal on the antenna. When you take the antenna and you bring it closer to the patient, if they're in the magnet, even if they're not, you bring it closer to the patient, the noise goes up. And the noise is from the patient, and it's from the molecules jiggling around inside the patient, right? And the patient's at a higher temperature, right? You can imagine you could cool down that coil. So put it in liquid nitrogen, the noise will go way down, right? Because the motion slows down with temperature. It's called thermal noise. But the patient, you can't cool them down, right? Too much. So you put it on the patient, they're like, 98.6 Fahrenheit or 37 Celsius, and that is the noise you're gonna see. And so that produces random signal on top of whatever signal you're trying to measure. So if I have an image and I take a line across the image, normally our images are like 512 by 512 pixels, say, and now I draw a line across the image and map out what is the actual grayscale value of each pixel as I'm going across. This one's close to 40, 90, 35, 70. So I'm just measuring those numbers that are in the image. You can see I've got a lot of random stuff going on with that pink curve, right? So what you can do is to try and reduce the randomness is just, let's take a look at this point, and we'll take 1, 2, 3, 4, 5 pixels in a line. The third one it's centered on that third one, and I just average those together and come up with a new value for this point. Okay, so instead of this value now, I have this value, and it's the average of that point plus these two and these two. All I'm doing is taking a window, averaging 5 pixels, move it another pixel, average 5 pixels, move it another pixel, average 5 pixels, and I produce this new profile, and it has a lot less randomness, right? It's closer to the mean value of the whole thing, and the randomness has gone down. And I've sacrificed spatial resolution for signal to noise. So when you present the image to a radiologist, they look at it and they go, I can't look at that. This is garbage because it's got too much noise on it. So it's all speckled and noisy. You can say, well, I tell you what, I'll smooth it for you. So you put some filter on that does this kind of averaging, and a lot of the noise goes away. But fine features also go away. If you're looking for a fine feature, it could be averaged away, right? However, bar none, on the CT scanners we have right now, radiologists always want you to smooth the data as opposed to see it at full resolution, is the situation we're in right now. Sure. Okay, so sure, it's a good question. So the question is there a limit to how much smoothing you can do, right? And yes, there is. And so if instead of 5, I went in here and said, I really want to smooth this thing out now, I'm going to take, 10 on each side and then calculate the average. Eventually, this line, this black line, which is this output from the smoothing, will be a flat, constant line. It'll just be constant. And at that point, you have a super signal to noise image, because you got no noise basically left, but you don't have an image either, right? So you just have an average value. So that tells you what is my average value of the entire picture, which is an interesting data point, right? So you just take every pixel, average the whole thing together. That's my average value, right? So that's the DC component of the signal. It has, you know how much stuff there is, you have no idea where it is, right? But you do know how much stuff there is there because you've added it all together, right? Um, however, usually right now, I would say on CT, we can make images that have at least twice the resolution that is always displayed to the radiologist. They want it smoothed out so they can feel more comfortable looking at the pictures. They want a more comfortable picture. And we'll see how you can reduce the amount of noise, right? Another way of making it better is just, well, if this is my noise, how do I just take a picture that has less noise? We saw you can cool a coil in MR. In CT, you use more photons. So I blast photons through a patient, and then I look at the shadow on the other side of the patient. If I use twice as many photons, I get a better shadow. It's less noisy. But what have I done? I can't keep doing that, right? Because I can't just keep increasing the number of photons. Eventually, you're just using too many photons, and too much dose is going to get absorbed by the patient in X-rays. X-rays they're called ionizing radiation, so they will break some molecular bonds and things like that and cause trouble. So you can use the simple window we just looked at, which is this red curve where I say, here's my 0 point. What's my new value for this pixel? Well, it's the average of 2 on either side in itself, and that's a simple averaging window. Or I could weight the value of the pixels around my target. So my target again is 0. I don't use this one. I use a little bit of this one, right? A little bit more of this. 50% of my signal is going to come from the middle one and then symmetrically. So now it has changed the shape of that averaging. It's not as severe as that rectangle. It's sort of centrally weighted. And then I can also put negative lobes out here. And what this will do is it'll enhance edges. And we'll see how that works. It turns out that what we're doing with this averaging is essentially like a convolution of this filter kernel, it's called, with the picture. You do that convolution and that smooths the picture, or it filters it. The way you can think of that also is if we take the Fourier transform of these functions, go into Fourier space, look at the spatial frequencies, all I have to do is multiply the Fourier transform of this filter kernel times the Fourier transform of the image, do that multiplication, inverse Fourier transform to come back to space, and that's equivalent to doing this convolution. So that's usually how it's done, right? It's because that's more efficient in terms of calculating, but we'll get deeper into that. Here are some filter kernels. This is a two-dimensional Gaussian kernel that has, most of the weighting is at the central peak, and then it falls off radially from that. So that's normally how smoothing is done, is with a kernel that looks something like this. It's pretty smooth. These kernels, if we do that same process, you can see here I've got a positive on one side and negative. This is actually, when you run that kernel across, it'll actually evaluate the derivative of the image in that direction. And this will evaluate the derivative in the vertical direction. And you can go to these higher order kernels. And unless you're looking for something specific that has a specific kind of shape, usually you don't use any of these kernels down here. But if you're trying to convolve through a picture and find something that has components like this, you can use these kernels. Here's a simple example in radiology. Can you guys see the images okay, or should we turn the lights out? Are you good? Okay. This is the starting original picture. If I convolve it with something that looks like this, that say this width is like 2 or 3 pixels, from here to the half height, it blurs the picture. And so these features right here are pretty well blurred out. Signal to noise is higher. If I looked at the average signal here divided by the noise, but I have eliminated a lot of features in the picture. Here, we're doing increasing edge enhancement. So that's in these filter kernels, that's the ones that have these negative lobes. So I edge enhance the picture, edge enhance it more, and now I edge enhance it so much that things that are relatively constant just go away. And the only thing left is this edge right here, right? And right here. So this looks a lot sharper than the original one because I have increased the power of these high spatial frequency components or these edges, and I get something that looks sharper. Again, on your phone, this is basically you've got a slider on your phone and you can say, make my picture sharper, and it will, take one of these filters and take your picture and make it sharper, or you can blur it. Depends on your goals, right, of your picture, for your picture. So talking about Fourier space, we're going to look at how do you reconstruct a function from discrete Fourier components. So back in your, freshman math, or maybe, I don't know, sophomore, you probably studied the fact that given any function that is basically continuous and smooth enough in certain ways, I can create that function by adding up sines and cosines with different amplitudes and phases, right? That's the Fourier theorem. Joseph Fourier came up with it looking at the distribution of heat in a bar. Like if it's hot on one side and cold on the other, what does that function look like? He figured out that you can create an arbitrary function from these sines and cosines, which were all solutions of this differential equation. So it's a really cool thing. And Fourier theory, if you want one piece of mathematics you should know in your life, and you should carry around with you and know it just like that, it's Fourier theory. Because everything in physics depends on Fourier theory, including high energy physics, including quantum field theory, all of the stuff. It all comes back to this guy Fourier, right? And it also means that when you walk around, you can see life as amplitude versus spatial position in your visual field, and amplitude versus time in your hearing, right? And then if you know Fourier theory, you also can say, well, what are the spatial frequencies in this pattern? Is there a regular thing that is a dominant frequency, right? And then when you're hearing stuff, the reason you know a flute is not an oboe, right? When the flautist plays a note, is that you do Fourier transformation in the hardware of your hearing, and it brings up certain frequencies, and your brain goes, oh, that set of frequencies and overtones is a flute. It's not an oboe, right? So, and that's how you know when you get on the phone, that's how you know it's your mom, right? It's like, we're pretty amazingly good at, your brain at specifically getting an imprinted Fourier spectrum and saying, I know who that is, right? So here's an example. Let's look at this dark curve here, this black curve. We're well on our way to making what's called a square function, square wave, right? So it goes to a certain value, drops down to a value, and then goes back up to that certain value. To make this function that's shown here, there's only 1, 2, 3, 4, basically sines and cosines added together with different amplitudes. And the amplitudes are shown by the relative height of the curve. So here's the first one, right? That's one sine wave. It has one wavelength here. So that's between a peak to peak, that's the wavelength of that sine wave. And then the next component, next highest frequency is this one, in which we have, it starts at this point with a negative. So we got 1, 2, 3 wavelengths of that sine wave. So we've got 1, we've got 3. The blue one is next, and we have, starts here at the peak. We have 1, 2, 3, 4, 5 wavelengths across there. And then the little one goes back to negative, and we have 1, 2, 3, 4, 5, 6, 7. So we have 1, 3, 5, and 7 are the frequencies of the sine waves that are added up, and their relative amplitudes are given by those heights. And when you add all that up, you get this black curve. If we kept going, instead of 1, 3, 5, 7, 9, 11, 13, 15, just kept on adding higher frequencies, this would approach a perfect square wave. It's still, it's an interesting thing when you look at discrete Fourier composition of functions, you're still going to get a little ringing on these edges. Even as you go to higher and higher frequencies, the ringing will be pretty well the highest frequency you include, and it'll be right at the edge. It'll go zing, 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 ring down, right? So it's hard to make it a perfect square. What happens at these edges here is you get a little ring down, right? That's called Gibbs ringing. And you'll see it in images. Like when you see a really sharp edge, sometimes you'll see a little ringing off the edge. That's called Gibbs ringing. So that's sort of the common sense way or sort of intuitive way of looking at Fourier composition of signals. Now we're going to look at, instead of the point spread function, we're going to look at the modulation transfer function as a way of quantifying what is the resolution of my imaging system. And we're back into Fourier space here. We have sine waves. Here we have basically a sine wave with, wavelength of 1. This one is 2. This one is 4. And we ask the question, if I was to send this sine wave through my imaging system, what would the output look like? So now I have a wall, and instead of having a constant image on the wall, just a flat background, I'm going to draw vertical bars on that wall, and they're going to be equally spaced. Okay, and so it'll look like this. So I draw those vertical bars on the wall. When I take my imaging system and I take a picture of those vertical bars, what comes out is it looks something like this, right? So I do see the frequency, that dominant frequency. I have a peak here and a trough and a peak and a trough, okay? So I can resolve this pattern. The amplitude between this, say this is 1 minus 1, this is a little less than 1, a little more than minus 1, the peak here. So it's diminished the actual amplitude of that oscillating function slightly. When I increase the frequency down to 56% of the, or I'm sorry, increase the frequency from 1 to 2, right? The output contrast goes down to 56%. So here's my function here. And then when I look at the amplitude of this bright thing, right, it's been diminished. And the amplitude of the trough has also come up. And so the distance or the contrast between this and this has been reduced to 56% of what it was up here, okay, or what it was here, like 1 minus 1. And then when I go to a higher frequency, this is 1 millimeter, this is 4 cycles inside a millimeter. This is very high frequency for imaging, medical imaging. It looks like this, and I barely have any contrast left, right? If I go to a high enough frequency, I have no contrast left. It basically is an average value. right? So the bars that I put on the wall that have this separation, when I take the picture, I don't even see that they're independent bars. I just see the average value inside this zone here. And that's the end of our resolution. We can't image any more than that, right? At any higher frequency. So this is called the modulation transfer function. And if we plot these values, it's 87, 56, and 13. 87, I diminished down to 0.87. At 2 cycles per millimeter, I went down to 0.56 here. At 4 cycles per millimeter, jump all the way to this frequency, I go all the way down to 13%. If I did this with finer resolution in these experiments, I would map out this curve, right? So low frequencies get passed through the system just fine. As the frequencies get higher, they get diminished in terms of the amplitude between the positive and minus. So eventually this goes down to 0, right? And I can't resolve anything higher than a specific frequency. And this function is called the modulation transfer function. And if you look at the spec sheet of a scanner, oftentimes they will tell you what the modulation transfer function is. They'll have measured it and they'll plot it for you. Say, this is our modulation transfer function for this scanner. Sometimes the manufacturer won't show you the whole function. They'll just show you, they'll say, we're down to, 10% or 0.1 at this frequency, at 4.3 cycles per millimeter. That's where we're at 0.1. And so they'll just give you that value. Some of them will say, oh, at 0.05, we're down here, because they want a bigger number here. Obviously, a system that has a big number for the spatial frequency, the cutoff frequency, says you can image things with higher resolution. Okay, so that's called the modulation transfer function. It's an important concept. It's a complement to the point spread function, right? And the reason you sometimes use this as opposed to just the point spread function is sometimes this thing has a complex behavior such that the point spread function itself has some strange complex behavior, and this, you can map it out. Oftentimes, this will be flat for a while and then roll off, right? It'll start rolling off at a specific shoulder frequency and then go down at a specific rate. How do you measure it directly? Well, this is a paper. You can go take a look at this paper if you want. And the purpose or the thesis of this group was that they have a specific new way of reconstructing CT data that extends the modulation transfer function out. So normal one would be down here. Theirs, they say, is going to extend out. So they're going to have higher spatial frequencies available. So you put this phantom, it's called, inside the scanner, and it has these parallel bars, right? So here you've got 3 bars, 4 bars, 5 bars, 6, etc. So they get closer and closer together. This is standard reconstruction. We'll zoom in here because they claim that at this standard reconstruction, they're down to a very low contrast between the high signal and the low signal. So they're sort of at the limits of the resolution. And with their tricky algorithm, they can make that look like this. And so the contrast is higher. So the modulation transfer function at that frequency is higher, right? And you can believe them or not believe them, but that's, you read the paper and decide whether or not you think that's going to pan out to clinical images. But this is a nice phantom, right? To actually physically do this experiment, right? That's what they're doing. They've just made this phantom, right? Interestingly, so here, this is called the modulation transfer function. Remember, it's in this space, which is spatial frequency. So this is cycles per millimeter. So it's like waves on the ocean, right? Waves on the ocean are peaks and troughs per unit distance. So if I look at a big wave, I say, oh, there's these really huge ocean waves. I have one cycle per 40 meters, right? That's a spatial frequency. And then these little tiny ripples waves are, one cycle per 5 centimeters or something. So that's a spatial frequency. If I look at patterns around the room, there's a spatial frequency like in those lights, right? There's divisions in the lights, there's divisions in the tiles, so they come up at a spatial frequency, right? It's like one thing per half meter or something like that, one cycle per half meter. And then certain patterns in nature or in, like, say, a rock garden, the rocks will be a certain diameter. And so when you look at the Fourier components of just that picture of the rock garden, it'll have a peak that represents the cycles of that diameter of the rocks, right? So everything in life has this, right? So so here's our relative amplitude that the imaging system passes as a function of cycles per millimeter. If I take the Fourier transform of this function, right? Here's that Fourier guy again. If I take the Fourier transform of this function, I get the point spread function, right? So if I have a really wide modulation transfer function that has high amplitude out to high spatial frequencies, when I take its Fourier transform, I get a very narrow point spread function. It's a sharp point spread function. If, on the other hand, my modulation transfer function itself is narrow, and then there are no spatial frequencies out here, my point spread function is going to be a big blob, right? It's going to be something that's big and mushy, right? And you can create phantoms. We just saw one line pair test phantom. Here's another one. This one's continuous. So if you built a function that has this structure, essentially you can stick it in your scanner and just see where do these lines merge and measure the spatial frequency at which you can't measure anymore. Okay, so that's spatial resolution in a nutshell. We're going to characterize it with point spread function, which is if I image a tiny dot, well, how big is the blob, right? If I take that blob, it turns out, and take its inverse Fourier transform, I get the modulation transfer function in spatial coordinates. Or I can directly measure how the amplitudes go down with spatial frequency by using phantoms that look, like this or like this. Okay. So now we're going to look also at how the amount of noise affects the image quality. And is there a way we can quantify the amount of noise versus the amount of signal? Ideally, we would like perfect signal, that is contrast between two things. So if what I'm looking at is an image of the heart, and there's the heart wall, the left ventricular wall, and then there's blood in the chamber, my imaging system will give me a signal that is appropriate for muscle that's the heart wall, and it will give me a different signal that's blood in the chamber. Those two signals, a lot of the time, they'll be quite different in CT because we'll inject contrast agent to make the blood very bright. And so now I have two signals. So that's my signal amplitude, is what is the difference between the muscle and the blood, right? Sometimes that is very subtle. So if you're looking at, again, remember we were looking at CT images of the liver. Sometimes the metastasis is different, but not by much, right? Just by a few units, it can be different. And so that's when the contrast is low. What matters really is what is the contrast divided by the noise, which is the uncertainty in a pixel amplitude. So if I have 1,000 pixels in the blood, I can ask the question, well, here's the mean value of those 1,000 pixels. What is the random scatter around that mean value for each pixel as I look at the blood, right? And so as you add more noise, this is a phantom. It has these, essentially they're cylindrical objects filled with different amounts of contrast. Contrast is a molecule that absorbs X-rays. And so you can create a brighter picture by putting a lot of contrast, or you can dilute the contrast to 50% and make less contrast, you know. But we're going to create a phantom that has these vials in it. They'll be filled with contrast. Those are background. Let's say that's plastic, and it has a certain CT number. This has a certain CT number based on the amount of contrast that's in this vial. And then as I reduce the concentration of contrast, the difference between the background and that signal goes away. So to make things simple, let's say this is water in the background. This is the highest concentration of contrast in water inside this vial. And then as I reduce the contrast, I go back towards my water signal back here. Eventually, if I have a vial with just water in it, I don't see any difference between the background and that vial. Now, the difference between this picture and this picture is when I took my image, I used less X-rays, and therefore there was more uncertainty in the number of X-rays I detected on my detector, right? And it creates a noisier picture. And then let's cut the X-rays in half again, and now I've got an even noisier picture, right? So obviously this picture is best, but the question is, like, how do you quantify how much better this picture is than this one? Right? And this is based on a detection task. So the question is, in this image, which one of these vials can I detect with, say, 90% confidence that it's there, right? Versus this. So the way you run that experiment is you know that there is a signal here. You know beforehand there's a signal here. So you put a little circle around this signal and measure the amplitude of the background, and ask, what's the probability given this amplitude, the amplitude of the background, so I have a difference, divided by the noise. What's the probability that there is a signal here? If that probability is like 98%, then you just say, yes, there's a signal there, and you're going to be right 98% of the time. We go to higher noise, and we do the same thing, and we still achieve a very high probability of detecting this vial given our simple measurement. When I go here, though, this one gets cut out. If I put a region of interest around that vial and I measure the signal inside the vial and I measure the background, I can't tell you there's a signal there. I can't be certain. It's like, you know, worse than 50-50 or something, or it's 50-50 basically. Say, I don't know if there's a signal there. And so this curve that encompasses all of those vials that I can detect, like with 95% confidence or whatever you want to set your threshold to, obviously if you set it differently, the curve changes, is called the contrast detail curve. If I have higher contrast, I can still detect them at a specific noise level, or if they're bigger, I can still detect them. And the reason is it matters how big they are is because you can average over that larger area, right? And so that's how oftentimes CT scanners are quantified, or these different contrast detail curves. Okay, so there's two features. One is the size or the spatial resolution. The other is the amount of contrast that is available. Right? And so how we evaluate what that contrast to noise is described on this little chart, little graph. And this is a histogram of the signal values in, let's say, our target, which is this blue curve. We'll say that's a brighter thing, and we want to detect something that's bright in a background of a darker thing, which is this green curve. Okay. And so the histogram tells you what the mean value is of the background. If I took all of the pixels in the background, which are these guys, the dark ones here, take all those pixels, right? And I average all of them, I will get this average value of the background. And the width of this histogram tells you the distribution of values around that average, right? So if the distribution is really wide, that means there's a lot of variability in the signal amplitude of the background. And that's quantified by this parameter sigma, okay, which this is the mathematical function that describes both of these curves. We have a sigma value for the green, and we have a mean value here. And now we look at our target, and it has a higher mean signal value, but some of the pixels inside our target actually have, pixel values that are less than the mean value of the background, right? They have a broad spectrum. And so the contrast to noise is defined as the difference between these two signals. So this is the mean value of A minus the mean value of B. So what is that difference? Divided by the sigma value. Now, if these two sigma values are the same, you're in good shape. You can just use that as your sigma, your contrast to noise. If one of them is wider than the other, you should probably use the wide one for the contrast to noise, right? So is that pretty clear? You can measure sigma because it's the mean minus every other pixel, right? And you square that and then divide by n minus 1 because we used 1 degree of freedom to calculate the mean. And that gives you sigma squared, this function. So you take the square root of that to get sigma. And then the mean, you all know how to compute a mean. You just take every pixel, add it up, divide by the number of pixels, right? So that's called the contrast to noise. How do you measure it? Practically speaking, is fairly straightforward. If you have a picture that has regions that are the same imaging intensity. So I need a big enough region to put a region of interest and say, okay, this is my target, right? I'm going to box in, so I'm inside my target, and I will take all the pixels inside that box, that region of interest. I'm going to calculate the mean, and I'll calculate the sigma squared, or sigma. And that gives me this curve. So now I have sigma and the mean. I look at the background, right? I calculate, I just define something that's all background, and I'll take the mean value over all those pixels and I'll compute the sigma value. If I make this region of interest bigger, I just get better, higher quality estimates of these two parameters because I'm using more points to compute them. But I also have to ensure that there isn't some feature or change in signal that's going to affect my estimate of the mean and the standard deviation. It should be in a region that is constant, right? Sometimes in a medical image, that's hard to find. You look around, it's like, what am I going to use as a region of interest to calculate the sigma? So you really want to find something that is constant. If you can't find something that's constant, if you have two images of the same thing, you can subtract them. And the only thing that should be left is sigma, right? Because you've taken all the features out, and you should just have an image, a noise field that is sigma. So that's another trick you can use, but you still need two images to do that. So, okay. So for most of what we're going to look at, you can assume that the pixels in a region of interest are going to follow a curve that looks like this. It's a normal distribution, it's called. This is one way of writing the formula. This is the Gaussian distribution. It's called a normal distribution. Another way of writing it is it's the Poisson distribution with large M. So you have a large mean, you'll get a function that's exactly like the Gaussian function. It turns out when you have very low numbers of photons, the distribution changes. We'll look at that in a minute. But most of the time, we're going to assume things have this kind of functional description. And so you can look at something like this as your contrast to noise. In X-ray, when we think about it and if we're taking an image, and in the introductory lecture, you saw that you have your patient standing in front of an X-ray source or lying down with an X-ray source. The X-rays go through the patient, and the patient casts a shadow, and you detect that shadow on an X-ray detector, right? The X-ray detector is an array of detector elements. You know, it could be 1,000 by 256 or something like that. So you now have a picture of that shadow. For each element in that detector array, you ask the question, how many X-rays did I detect when I flashed my X-ray to take the picture? And in CT, the interesting thing is that number can get pretty darn low per detector. So if you turn the X-ray intensity down and down and down because you want to minimize the dose, eventually you get to a situation where inside a single detector, you may not detect any X-rays. You just didn't get one, right? Or you got one, or you got 5. And so we're actually operating down at a level of X-ray intensity for which the actual numbers you're detecting are quite low. And obviously, at that point, you have a different distribution than a symmetrical one. So for this distribution, I turn my X-ray intensity on, and I get a mean value of 10 photons per detector. The distribution of values I'm going to see if I look over all my detectors and it's a constant shadow, right, will look like this. Not many will have 0 photons. Virtually everybody's going to have a photon, but only this fraction will have 5. This fraction will have 15. So it's a nice symmetric Gaussian function, normal function around 10, right? However, if I then click down my photon intensity, right, I'll get something that looks like this. So if now my mean value is 4, I'll see this relative intensity. It still looks kind of like a symmetric Gaussian function. Now I click down my X-ray intensity so that in some of my detectors I'm getting 0, and some I'm getting 1, and some I'm getting 3, 4, and 5. Then it's not going to be a symmetric distribution, right? Because you can't go less than 0. This is the probability of having events occur. So there is no negative event, right? So basically, it is a one-sided distribution that comes down here. It's called a Poisson distribution. And if you are going to model successfully a CT scanner at very low dose, this is the noise model you need to put in, not this, right? So that's for low dose CT, you need to take into account the fact that the distribution of photons detected is this one-sided thing. Okay, so if we look at, just to give you a gestalt of what different SNR values look like, let's start with SNR of 1. So that means the signal difference between this patch and the background. If I look at the mean of this and the background, right, I get some value. And then I look at this sigma value inside there, divide that, I get 1, okay? So the step up in contrast is 1 noise unit or 1 sigma value. If I look at the profile through that, you can see it's got a higher mean across here and then back down, but it's not that obvious that there is a signal there at all, right? So, but that's what signal to noise of 1 looks like. If you have a big square, you can see it because you can average, your brain averages over that field, right? So you can see it. 2 looks like this. A half looks like this. So, we're way, way down. In radiology, basically the threshold for signal to noise that a radiologist or any human is comfortable using is 5. That's called the Rose criterion. And the Rose criterion means I can put an ROI over that patch. And if I get a contrast to noise of 5, I am going to be right about 99% of the time that there's something there. And so that's what the Rose criterion is. Here, this shows there's differences in how noise appears in images between MRI and basically the rest of the scans that we're going to be looking at, which is nuclear medicine, PET, CT, and echo. And in MRI, although multi-coil MRI gets a little complicated in terms of the noise model, without taking that into consideration, if I look at a signal level of, say, 1, 10, 20, something like that, the noise level on each one of those is the same in MRI. Okay. In CT, as the signal gets brighter, the noise level itself also gets higher. Okay. And the reason for that is that what does it mean to have a bright signal in CT? It means more X-rays were absorbed, right? And so when more X-rays are absorbed, this uncertainty of whether or not there's an X-ray in a detector goes up, right? Because the number of X-rays you're dealing with has gone down. Right? So ironically, the bright things in CT have higher noise on them than air, for example. Air, which has a CT value, a Hounsfield value of -1,000, is essentially the maximum number of X-ray photons that you're going to see in your detectors for that scan, because there's nothing in front of the detector, right? It's going through the air, hitting the detector. So that's the highest number of photons you're going to see. And so that's also the highest precision, value you can estimate because you've got the most photons there. As you get lower and lower photons, so in cardiac imaging, you inject a contrast agent, it makes the ventricle really bright, but it absorbs a lot of photons when it's going through the ventricle. And so when you get to the detector, you're dealing with fewer photons now. Okay? And so the noise on those bright signal goes up. So unlike MRI, where if you look at a field of view, the noise is pretty well uniform everywhere in the field of view, unless you're using some complex multi-coil thing. In X-ray, the noise will change as a function of position and brightness. So here's, I go back here, yeah. So here's a signal. I don't know if there is a signal on here or not. Okay, if you look at that, do you see any signal there? Does anybody see a signal? I can't really see one. Can you see one? No. No, I can't. But there it is. Okay. So basically, if I reduce the noise and go there, now you can see the signal, right? Right. So that's what that signal looks like. So here's the noise level in the background. You've got this mean value up here, and it basically the contrast to noise is achievable for you to see. So do you see a signal on this one? No, I don't really see a signal on this one. Now do you see a signal? Right? What's that signal? Let me go back, play it again. One of the problems about my PowerPoint, for whatever reason, is the movies screw up when you go to display mode. Say we're going to do this. So there's a couple of things happening there, right? One of the things is we now have time in this. And so as your brain, your eye brain are watching the pixels, you're computing in your eye brain the average value of pixels over time, right? So you can sort of average in the time dimension. Secondly, I guess this comes from the fact that we're like hunters or something, but because that thing's moving, it's easier to see, right? So basically something moving across the field of view you perceive with better. So this signal to noise is exceedingly low. This is down about that 0.5 or 0.25 or something like that, but you still see it as a human, right? Which is kind of interesting. So it depends on the situation. In echocardiography, if you look at a still frame that is from echocardiography, it looks pretty crummy, actually. A lot of the pictures when they're just stills don't look good at all. But in echocardiography, you can make quite easily 30 frames a second, right? And when you do that, and the heart is moving, and you're imaging that 30 frames a second, all of a sudden features jump out at you because of this averaging in time and the fact that things are moving. So we'll see examples of that in echo. When you look at a still picture and then you turn on the movie, it looks much better. Okay. So that's what that signal looks like. The profile of one of those looks like that. And that's what you can see, right? So it doesn't look like there's any signal there, right? But it basically is a reduction in the RMS, or the noise level, is essentially what that signal is. It had the same roughly mean value, but I think the noise level was reduced. Okay, behind that. Okay, so there's a couple of definitions here: accuracy versus precision. And this measurement, say this is our actual target value for our system, is this. This measurement, it turns out, is highly precise in that you get basically the same number every time you do the experiment. It is not accurate because you're missing the actual true value, underlying value of the thing you're trying to image. So if we're trying to image the Hounsfield units of liver, we get the same value all the time, but the value itself is off to the side, right? That's called high precision, low accuracy. High precision is a good thing because with the accuracy, you can imagine that what could you do? You could basically calibrate and say, well, when it's over here, I actually know this is what the thing is. And so you just calibrate your system to bring the numbers back. And so now you've got a precise and accurate system. The mean value of all these dots is right in the middle. So it's accurate, but it isn't precise. It has a broad noise level, right? This is what you're after. And, this is the worst of all worlds, is that not only do you have a lot of noise, you're not even on the right number. You're not accurate. So the question is, how do you evaluate these different imaging techniques? And one of the things you have to wrap into it is the behavior of the human who's going to look at the data, okay? And this is from a paper quite some time ago. This is 96. They took 150 echo studies. These are called stress echo studies. And so they stress a patient, take echo, and then ask the question, is this heart ischemic or is it not ischemic, right? If the functional movie of the heart goes a little wonky, like you get a piece of the heart that isn't contracting as much, you call it positive. You say, yes, this patient has disease. This stress test is positive. If you don't see that happen, you say it's negative, patient's okay. They gave 150 cases on a disc, to 5 different echo centers and asked them to read them. Okay, that's all I did. Just like, here it is, read it out. Center 1 said 102 of the patients, of the 150 patients, were positive. They had abnormalities, and only 48 were negative, did not have. Down the road, Center 2 said, oh, 62 of those patients are positive, 88 are negative. Down the road farther, this clinic said 38 of these patients are positive, 112 don't have heart disease or negative. 71-59. So you see the problem, right? It's not the picture isn't the only source of noise here. It's the humans reading the darn thing. These people, why would these people have way more positive scans than these people? Has anybody got a hypothesis? Why would I have way more positive scans here than here? Go ahead. The technician kind of is out of the picture because the scan's already taken, right? These are the same scans. So it's the same data. So I think what's going on here is these people are in a center where when people walk through the door, more often than not, they are positive when they walk through the door because it's an emergency center or something like that. These people, maybe they're in a private clinic in the suburbs. Most of the people that come in are just like worried, but they're normal. So they call way more people normal. Their different thresholds adapt to whatever environment they're in, right? If you want to be super cynical about it, right, you could say this is a center in which if you're positive, you get sent to our cath lab and we'll cath you. Whereas this center doesn't have a cath lab. There's no reason to send people to a cath lab unless, they're super positive. Whereas this, they would have a much lower threshold to send to the cath lab. These people much higher. So those are human behavioral traits. It's not just the quality of the human reader, it's also their own personal environment and bias. So when you're trying to evaluate 2 different imaging techniques and saying, well, imaging technique A is better than imaging technique B, and you've got this kind of noise on top of that, how are you going to differentiate those 2 things, right? It's a little bit tricky. You need to get rid of this observation bias in order to evaluate the efficacy of your imaging technique. And we'll come back to this. Let me see what we got here. Okay, so image quality, including the reader. Normally what you do is you come up with this confusion matrix, okay? In order to test an imaging technique, you need to know the underlying truth of the patient. Are they actually sick or not? Right? So that's a complicated thing. You usually find that out later down the experiment or later down the clinical care of that patient. They wind up to actually be sick. So you come back and look at this table after you know who actually is normal and who actually is abnormal. It's the hard part of doing these is you need ground truth, right? The observer response is the combination of your picture with those people reading the picture. And so true positive is what happens when I call a patient abnormal and they truly are abnormal. So that's a good thing. False positive is I call a patient abnormal, but they are not. They are actually normal. Okay. So if you go back here and ask the question, who's going to have the most false positives of these clinics? Well, I think it's probably going to be this one. They're calling a lot of people positive. So they're probably calling a lot of false positives, right? Or more than the other clinics. True negative is another good thing. You call them normal, they're normal. Okay. False negative is a really bad thing. You miss them. You call them normal, they walk out and they are not normal That's not a good thing, right? So that's called a false negative. And we're going to define sensitivity and specificity. So sensitivity is when you call someone true positive, or if we have a whole group of patients, I say, how many do I call true positive? I have that number. How many divided by the total number that are true positive plus the number that are false negative, i.e. the positives that got called negative. So this is the total number of actually positive patients, and these are the number you called. So if you only get 50% here, that means your sensitivity is 50%. I only gathered up 50% of the positive people and called them positive. Specificity is exactly the same thing, but in the negative direction. So you count how many are true negatives divided by the true negatives plus the negatives that were called positive. And that's called specificity. Okay. You can see what happens if here's the distribution of, here's my decision parameter. So this means I'm going to say if anybody, I'm going to measure something. If it's above 50, I'm going to call that person abnormal. If it's below 50, I'm going to call them normal. Okay. And so this could be some quantitative function you measured of the left ventricle, like its ejection fraction, or you measured the wall thickening or something like that. And you set a threshold and say, anybody whose ejection fraction is above 48%, I'm going to call normal, right? Right. So we set that threshold. This is the distribution of normal people that walk through the door. This is the distribution of abnormal people that walk through the door for that parameter that we're measuring with our imaging technique. And here's the threshold. This area under here are the true positives. I call them positive and they are positive. This area, this tail here, is the false positives. I call them positive, but they came out of the normal group. And so that's the false positive. This group is true negative, right? Under the blue here, below the threshold, and this is false negative. So these are coming out of the positive distribution. Because they're below my threshold, I call them negative. I get it wrong. Okay. So that's the definition graphically of where those calls come from. If you have these underlying distributions, you're done. It's a good thing, right? What you can do, remember our people who were calling a lot of positives, their threshold was obviously set where? Down here, right? So they were calling a lot more positives. So they were pushing this threshold this way, right? And getting more people in the positive bucket. And then the ones that had 38, they pushed their threshold this way. They got some abnormals, but a lot of people were in the normal bucket. So what is independent of the radiologist or the cardiologist viewing the data are these underlying distributions. And so what you can do is you can set different thresholds and ask, what is my true positive rate and false positive rate as I change that threshold? If I call basically the positive rate. So here's my false positive fraction, right? So 100% false positive means my threshold is all the way over here. I push that threshold this way, and what happens is my false positive fraction decreases, but also my true positive fraction also decreases. Ideally, if these two distributions were entirely separated, right, there was no overlap between them, this curve would go all the way to this corner and then drop down. This is called a receiver operating characteristic curve. And most of them look like this. They go out like that and then curve down this way until finally your threshold is all the way up there. You're not calling anybody positive down here. You're not getting any false positives, but you're not getting any true positives. So the question is where, when I move my threshold back and forth, I move along this curve, right? And the area under this curve is often used as the relative indicator of the performance of the technique. So if you decide, oh, I'm going to change things, I'm going to add this new parameter to my decision, and the AUC curve moves farther to that corner, then you've improved the test. And people give the area under this curve as an indicator of the performance of the test. We'll review that again when we start on Wednesday. It's a very important concept, not just for imaging, but for virtually every test that's done that is dependent on threshold. You want to get rid of the threshold dependence and look at the whole curve is what you're doing here. Okay, great. Well, see you on Wednesday. I'll stick around. I don't know if they've given us the room for afterwards. I asked for it last year. It didn't happen. So we'll see what happens this year.